Okay, I just mentioned this thing about how to sculpt an elephant. I just made some pictures. One of our colleagues in radiology was just, I don't know if he meant it really or just made fun. We were asking him, how do you find the boundary of your tumor? He said, well, I look at the whole image and this is liver, this is kidney, this is bone, I remove all of that, and if anything remains, I examine if that is a tumor, and then I'll say that is a tumor. Then I remembered this joke about how to sculpt an elephant. So somebody asked this person, this is in Mamallapuram, somebody went there and asked, oh, how do you make all these beautiful sculptures? How do you sculpt an elephant? So he's making that there, it's not so easy, but the algorithm is find a big rock. And this is also from Mahabalipuram or Mamallapuram. My nieces and nephews are sitting under that big rock. It's been there for a long, long time. I hope it's still there. And remove everything that does not look like an elephant, and that's what you get. So, just for fun. Okay, that is segmentation. Now back to real stuff. So next chapter is on analysis of shape. We have completed the image processing steps. We said in segmentation, the output may or may not be an image. If you cut a piece of an image and give it, then yes, it looks like a picture. But if you just draw the contour or give the fuzzy membership, it's not anything like the original image anymore. But the next step, we go away even from that. So the output of the remaining algorithms could be some features, some numbers, such as when you apply shape analysis to a contour, you're not giving a contour back, you're giving some numbers back. And those numbers could be normalized to the range 0 to 1 or 0 to 100 or whatever, or could be open-ended. Depends upon the design of the algorithm. So why do shape analysis? There are several human organs that possess readily identifiable shapes like the heart, but then the heart is not like this, or you do that, well, it's not like that. The heart has a different shape. And kidneys, the brain, the bones, and in most cases the same average shape holds. That's how they make all these so-called ready-made dresses. We have certain ratios that are almost constant for most of us. But with the kidneys, some say kidneys are bean-shaped, but then there are kidney beans that are kidney-shaped. So which one comes first is up to you. But diseases can affect the shape and structure of organs. Morphological changes can occur due to diseases. Or there could be a tumor that pushes and somehow presses against some organs and their appearance is changed, like that neuroblastoma tumor I showed. So what are these shapes? And why is shape important? Even in abnormal situations such as masses and calcifications, there are differences between benign and malignant conditions. Benign is not normal. Benign means some disease that is not cancer. Malignant means cancer. Well, this also started misbehaving now. Okay. Most benign masses, I have shown some examples, appear round and well circumscribed with smooth and sharp borders. Sharpness is not of concern right now here. Some benign masses may be macrolobulated, big lobules. Malignant or cancerous tumors are typically ill-defined, meaning they're not very clearly separated from the background visually, and possess rough or stellate star-like shape with strands and spicules appearing. Now, previously the word stellate was used, stellate meaning looking like a star. But then star is a beautiful thing with all these songs and so on. They said, no, tumors are not beautiful things, they're not stars, so they tried to remove that word out. So it is not stellate, but spiculated. But most of the grammar, spelling correction software in Word and other things, they don't know spiculated. I write spiculated, it changes to speculated. And I write tabla in my music, it changes to table. So spiculated. Spicule means something that is radiating out, finger-like protrusion. Some malignant masses may be microlobulated, small lobules. So shape is a key feature in discriminating in these cases and also in pap smear tests. But biological entities exhibit a broad range of variation or variability around some general shape. They're not all round. There's some variation around that. They're not all spiculated. Some may have a few spicules, some may have many spicules. The number of spicules is not important, but the fact that it is spiculated. Imaging geometry, 3D to 2D, and superimposition of multiple structures in the image, in the object rather, in the breast. When you compress the breast, there could be several fibroglandular tissues and ducts, and if there is a mass that is round, if these superimpose in the image, it might look like spiculated. So you must be able to separate the mass from the other confounding or overlapping structures. So these factors affect shape analysis. Still, shape analysis is useful, as you will see. So how do you represent shapes and contours? Typically, we deal with closed contours. So you go around and come back to the starting point. So the XY coordinates of the pixels along the contour. You don't normally keep track of the gray value or density along the contour, just the shape. So it's a binary image, if you want to call it so. So a contour with endpoints could be written as xn, yn, n going 0 to n minus 1. Not exactly an image, but it needs 2D for display. So you could show it as a binary or bi-level image. Basic things. A point of reference is a centroid or center of mass. Many dictionaries don't recognize centroid. We use it so often. Center of mass is used by some people, some researchers. Centroid doesn't seem to be commonly used, and dictionaries don't recognize that. But anyway, average all the x coordinates, average all the y coordinates, that's a centroid. And that could be a good reference point in shape representation. If you take the distance of every contour point from that centroid, xn minus x bar square, yn minus y bar square, and that's just the Euclidean distance, then you can express a signature of the shape as a 1D function, this dn. And you can plot it as a signal, and you may apply signal processing algorithms if you wish. You can also define a radial distance signature by drawing from the centroid a line and find where that line intersects the contour and get that distance, and go 0 to 360 degrees and then plot that distance. But then if you have a rough spiculated contour, and if you draw a line from here, it could intersect multiple points on the contour, then that method fails. So which one of those will you take? So that has limitations. For irregular contours, such a signature may be multi-valued for some angles, meaning multiple intersections with the boundary. So going around the contour more than once generates the same signature, so it is periodic, which means you can use Fourier series instead of the Fourier transform, and there is a notion of harmonics. Going once around the circle is one cycle. If you go again, it's the same thing. But then if you break that signal into components using the Fourier series, you have other harmonics of that fundamental frequency. So here is a representation of a contour, the centroid x bar, y bar, and z0 equal to x0 plus jy0. That's the starting point, point 0. x0, y0, x1, y1, x2, y2, and so on, xn minus 1, yn minus 1. You want to go clockwise or counterclockwise, it depends upon your convention. Now, z0, z1, z2, they are complex representations of the x and y coordinates put together as a complex variable. That is useful in computing the Fourier series that we will see later. The distances I mentioned from the centroid, d0, d1, d2, dn minus 1, they form what is called a signature, a 1D function. So this is a macrolobulated benign mass. It's not a circle. If it is a circle, this will be a straight line. The radial distance will be the same for all points. But because it is varying from here, small and long distances and so on, if you plot it, you get this sort of, not a sinusoid, but something like that. This is called a macrolobulated mass. It's not a circle, but you can say there are 3 lobules, maybe 1 and 2, maybe only 2. Maybe this, I don't know if it is a lobule. Maybe this is a lobule 1 and 2 and 3. So 3 big lobules. And you get a low frequency signature. Whereas if you take a highly spiculated malignant tumor with so many protrusions, that's a centroid, you plot that function dn, you get so many variations. The number of points is different. Here it's more than 3,000. And here it is about 800. That doesn't matter. You normalize, call this 0 to 1. The size of this doesn't matter. You throw it out somewhere. So normalize, divide by the maximum and make that axis 0 to 1. Going once around the contour is 1. This distance is some distance, some number, depends on the sampling resolution. It's not important. The shape is important. The value of that distance is usually not important. In the 1960s, a chain coding method was proposed by Freeman that was used for many years. It's not so commonly used nowadays. The question is, how do you efficiently represent a contour in terms of its coordinates? So you start from you take up some arbitrary starting point, and then they select a direction of traversal, clockwise or counterclockwise, and use a code to indicate the manner of movement to go to the next point on a discrete grid. The movements are either with 2 bits, 0, 1, 2, 3, just left, right, up, down, or using 3 bits, including the diagonal 0, 1, 2, 3, 4, 5, 6, 7. So to represent this, depending on which one you choose, you need 2 bits or 3 bits per step. But this will be a coarse representation. So coarse representation, and the others are given relatively as to how you moved. So to reconstruct or plot the contour again in the correct coordinate, you need the starting point. If it doesn't matter, you can draw it using just the code. So the chain code facilitates more compact representation and gives you some data compression. But nowadays, that data compression is not of interest, but what you can derive from the code is important. So you require only 2 or 3 bits per contour point. So there are a few advantages. The code is invariant to shift or translation because the starting point is kept out of the code. To a certain extent, the chain code is invariant to size or scaling. Contours of different sizes may be generated from the same code by using different sampling grids. You're given the code, you are given this step as to this way or that way, but what should be the step size? You make the step size bigger, you get bigger and bigger contours of similar shapes. Not exactly the same, but mostly the same. A contour may also be enlarged by a factor of n by repeating each code element n times. So instead of changing the step size, you may say, I will do the same thing twice or thrice, and that also leads to enlargement or expansion. It may be shrunk to half the original size by reducing pairs of code elements, averaging to single numbers. But then, what is the average of these? You don't have that in between. If you have 1, 1, 1, fine, you can keep just 1. But when there is a change in direction, then there is an issue with that kind of averaging. The chain code may be normalized for rotation by taking the first difference, like a derivative, and adding 4 or 8 to negative differences depending on the first or second code. And rotation of a given contour by n times 90 degrees in the counterclockwise direction is achieved by adding a value of 2n to each code element, followed by integer division by 8, and addition of an odd number of Addition of an odd number rotates the contour by a corresponding multiple of 45 degrees. So you can achieve rotation. The length of the contour may be computed, the perimeter, by taking the number of codes and multiplying by the step size in the first case. In the second case, for the odd codes, you need root 2 because you're making a diagonal step. There are a few other properties. You can achieve reduction, check for closure, check for multiple loops, and so on. So in some of our projects, when the radiologist drew contours of masses with, as I showed here, 8,000 points or so, a contour like that is very difficult to draw on a digital a display looking at the mammogram. You draw that using a tablet, but then sometimes there could be some small tremor in drawing, and the contour could sort of loop on itself. And we need to get rid of all of that and clean the contour before further analysis. So it is one closed loop. You don't want it backtracking and having these little protrusions or loops. So the Freeman chain code can facilitate checking for multiple loops and also get the area and so on. So here is an example. I have prepared a better illustration. I don't have it here. I can show you later on if you want. So assume that there is a real contour, something like that. If you were to use only horizontal and vertical movements starting from here, then the code is 0. The next point is this. Let me see. Instead of this, I do have the other one. Okay, this is the new edition. I did a different illustration. So this is the dashed line is the original contour on some piece of paper, and this is my grid I have superimposed. So I take that as the starting point, and in this case, this is the starting point here, this solid one. So from here I go clockwise. So it's 1, 1. So this point is approximated by this point. That point is approximated here on the grid. So the real contour is that shape. So if I use only these 4 directions, that's the closest approximation I get. So the code is this. From here, 1, 1, 1, 1, 1, 0, 1, 0, 3, 0, 0, 0, and so on. So that is the chain code. For the same contour, if I now allow the diagonal connections, I get a better representation. As you can see, the overlap between the solid line and the dashed line, which I was missing in the first case. As I started developing more and more illustrations, I learned all these tools a little better and better, graphic tools. So here, the same vertical is 2, not 1. So 2, 2, 2, and so on, and 1, 1. Now you have this approximated better. There is a diagonal here and there. So the diagonals give you a better matching of that shape. So that's the code. We'll skip this part. So given a contour that is complex with so many protrusions and incursions and excursions, spicules or lobules and so on, how do you break it into parts so that you can analyze each part and characterize each part? Segmentation of contours or breaking a contour into parts. You would want each part to be piecewise continuous, or break the entire contour into a set of piecewise continuous curves. For that, you locate the points of inflection. And if you consider this function f of x, let the contour be represented in this fxy format, and let these primes indicate the order of the derivative, single prime, double prime, triple prime for the first, second, third derivatives. A point of inflection on this function or curve in 1D is defined as a point where the second derivative changes its sign. And to obtain the second derivative, you require the function fx and f prime x to be continuous and differentiable. So there are some conditions required. And then for the point of inflection, these are the conditions. F double prime x is 0, f prime x is not 0, and f double prime should be 0, and f triple prime should not be 0, the product that is. So those define a point of inflection in the 1D curve. Now you extend it to 2D. I thought I fixed this. That should be bold. So if you have a contour capital C here, x and y, and a 2D contour now with n points, then the conditions are the first derivative cross the second derivative must be equal to 0. The first derivative cross the third derivative must not be equal to 0. And they turn to these equations in the partial derivatives in the x and y directions, similar to the 1D case. So solve these equations, you find points of inflection. The problem is contours drawn by hand or obtained by segmentation techniques have some artifacts. And those artifacts can give you some false points of inflection. You get too many points of inflection because the curve is jagged somewhere. So we take a derivative, xn plus 1 minus xn minus 1 divided by I, and then average that over a number of points along the contour. So we smoothen the contour by applying a low-pass moving window filter along the contour, and then compute or determine these points of inflection. Olivier Minute from France came and did some project with me, and he wrote some of this code and developed the algorithm. The value of m, the moving window for filtering, is an issue. Number of inflection points detected as a function of the number of differences used was analyzed to determine the optimal number of points. After a certain amount of filtering, the number of inflection points detected did not change. So that's what we will take. So here are the points of inflection on a speculated tumor boundary as drawn by Dr. Desatel. Now there are some here they're almost straight, but still, if this is concave, curving inward, this has to be convex. There is a small curvature, so there is a little bit of waviness. So these points were detected. If you do more smoothing, it is possible to get rid of these excess points, but you may lose some real points of inflection by excessive smoothing. So we kept this. So filtering, beyond a certain amount of filtering, the number of points of inflection remained the same. If you don't filter, we were getting 1,000 points. With filtering, it reduced to how many? 58 points. The contour has a few thousand points. Now in between each of these, now you can say this is one piece, this is another piece, that is another piece. So what do you want to do? You could try to model each piece separately. You can't model the whole thing as one geometric shape. In one of our projects, we said we will take these points of inflection. We are breaking the contour into concave and convex parts, or incursions and excursions. This is incursion into the tumor. This is excursion, or going out of the tumor, protrusion. And Dr. Desertel gave us a very basic idea that if a mass or a tumor is benign, it is usually solid and has nearly a smooth round or oval shape. No concavity, and especially if there is a convexity, there must be a concavity. The whole thing is convex. There could be small artifacts. But if it is malignant and spiculating, there is a protrusion, and there are multiple protrusions, and between protrusions there must be a concavity. So the presence of concavity is an indication of malignancy. So we said we will break the contour into these parts. The black parts are all done automatically. The black parts are concave. You measure the length of all the concave parts, you know the perimeter, add the rest, and get a measure of fractional concavity. How much of the contour is curving inward? And for this case, it is 0.47. We have superimposed the contour on the original image here. The contour was drawn by the radiologist. We couldn't get such an exact contour by any segmentation technique. We got some approximations. This is benign, what is called macrolobulated, 3-4 big lobules. It's not a perfect circle, so in between the lobules there will be small parts of concave segments. So concavity is 0.16. So that turned out to be a good discriminant variable or parameter. Polygonal modeling or approximation of contours has been around in the literature for some time. There are a few different algorithms, but we found limitations in many of these algorithms. Pavlidis has some, and Ventura and Chen have proposed some. And they applied this not only to closed contours, but also open contours like signals, ECG signals and so on, handwritten numerals. So you could approximate various contours, open or closed, by fitting polygons to parts. Now, how do you get the parts is another question, but we did our partitioning as I showed just now. So in our work, a polygon is formed by using the points of inflection. Connect the points of inflection, but that's the initial step. And then you modify it iteratively. I'll just use all of this, I'll just show using this picture. So this set of points of inflection on that contour I showed earlier. Certainly this is not a good polygonal model. These are all straight lines. So the initial number of sites is 58. So now the algorithm says take one of the sides of the polygons and compare with the actual contour between those 2 points. If the distance between that line and the maximum distance between this line and the contour, which is maybe that, is more than some limit, 0.5 millimeters, 0.25, whatever you want, then you say that is not good. And you put another vertex of the polygon there, where the distance is maximum. So the number of points is increased, the order of the polygon is increased. In this case, that distance is very small, you don't have to do anything. Here, that distance is large, so you would want another point there. So keep doing that, and iteratively. So you may put that, but even this may be large, so another point and so on. And we haven't marked all the points here, but the straight line is there. There are 146 sides there. And that is a better approximation in terms of polygons, or one polygon, not polygons. So you see the actual contour and the sides of the polygon. Okay? So the iterative method converged within 3-4 iterations. Starting from 58, it reached that 140 something in 4 iterations. 1, 2, 3, 4, 5. Yeah, there. That's the end. For a benign, the contour of a benign mass, the number of initial sites is 14. The number of sites after convergence is 36. We don't need that many. It's not as complicated as in the other case. So that is modeling using a polygon. Now, Minute said, well, why a polygon? Let's use parabolas. Now, polygon is also approximating the contour well, but you need so many segments or so many vertices. In parabolic modeling, we take each of those segments between points of inflection and fit a parabola. And use the parabola, go back here, this here also. So that is a parabola. This is a parabola. But they're all rotated and displaced wherever. The aim in this case, in the first case, was to approximate the contour fully, so that there is a mapping of the original contour to the polygonal model. In the case of the parabolic modeling, we didn't want reconstruction. We wanted feature extraction directly. So for each of those segments, you fit a parabola. But because they are rotated and shifted wherever around the contour, some processing was required. So consider a segment of the contour represented by xs, ys. S is the variable along the contour. The parabola is y equal to ax square in the transformed space capital X, capital Y. A controls the narrowness of the parabola. The larger the value of A, the narrower the parabola. In the case of, I mentioned that in the case of malignant tumors, we have narrow protrusions, narrow parabolas. In the case of benign masses that are macrolobulated, the lobules are big. So the value of A should be the opposite. Should be larger the value is narrower, so it should be smaller. So theta and the shift are the parameters required. So xs is capital Xs cos theta minus ys sin theta plus c, and ys is a similar function. So rotation and displacement, that's all. So you go through all of that, and then you get these equations for the parabola, and then you want to take the derivatives and solve for all of these equations, and finally you get 2a cos theta is that. So that's one equation. Then you get 2a cos theta is y double prime s. So you can solve for these parameters a and theta, and then you have the transformation. So you got the parameters of the parabola for each one of them. The problem is you need the derivatives, and again you need smoothing. You saw the original contour was fairly rough. There were little variations that are not important. So you need to get rid of them. So before taking the derivatives, you need to apply a smoothing filter or compute multiple derivatives and average. You smooth the signal and then contour and then take the derivative, or take the derivative and then filter the derivative values. So benign masses being oval or macrolobulated should have a small number of parabolic segments with small a. And larger standard deviation A for malignant tumors. There are multiple parabolas with various values. So they should be So we use these statistics of the parameters, and we got 76% accuracy with 54 contours. Our database only had 54 contours at that time. Later on, we expanded the database. So in this case, we didn't put the parabolas back. If you were to display there, just a bunch of parabolas. There's no need to plot them. We just wanted the parameter A. Theta is not important. It's just where it was located. And the displacement is not important. So there's only one parameter for each parabola. How big is it? and how many of them are there on the contour, and what is the standard deviation or variation of A around the contour. So very simple, gave 76%. Now I'm quoting some results in some cases. It doesn't mean this is the end of it. This is one representation and one set of parameters. 76% is not good. So you want higher accuracy, bring more and more and more parameters from different perspectives. Not the same idea, but different ideas. So then, by combining them, as long as they are sort of independent in perspective and in the way they are computed, you will get better and better results, as I'll show later on. I'm showing one method at a time, but that doesn't mean one is good or adequate. When you have some contours or some extracted patterns, not necessarily contours, but some tree kind of a pattern, then you may not want all of the pixels, but simply a skeleton or a thinned down version of that to do further analysis. A skeleton is like the medial axis. There's a transform known as the medial axis transformation. So a skeleton of this would be just one line going through in the middle. A skeleton of this would be just the rim. But what is the skeleton of this? It's a thick object. So you will have the middle line, but then there are these variations in shape. So then the skeleton becomes a little bit more complicated, as you will see. Objects that are linear or oblong, or structures that are branching patterns like blood vessels, may be characterized well by their skeletons. You don't need all of the pixels. The skeleton could be obtained by what is known as the medial axis transform, or a thinning algorithm, or by morphological image processing. We're adding some morphological image processing techniques in the next edition of this book. The medial axis was proposed by Bloom, and it says the given image is to be binarized first, of course. You have detected the object. It's a binary image. So let those binary pattern pixels be denoted as B. Let C be the set of the contour pixels of B, and let Ci be an arbitrary contour point. So you want to remove all points that satisfy certain conditions. For each point B in that object, capital B, a point Ci is found such that the distance between the point B and Ci, d BCi, is at its minimum. If a second point is found such that C equal d BCk is equal to this, then B is a part of the skeleton of capital B. That is, you're in the middle. There are 2 points on both sides having equal but similar, we say, in practice. Otherwise, B is not part of the skeleton. So you have to find a line that's somewhere in the middle of that segment and do it for every pixel. There is a thinning algorithm from Gonzalez and Woods, and they have given references, and I have the references in the book. So if you have this pixel being processed and its 8 neighbors are numbered in this order, the other way, 2, 3, 4, 5, 6, 7, 8, 9. P1 is the center pixel. Then there are some conditions that are checked. They're all binary, 0, 1. So for a contour point P1, for deletion, the following must be met. The number of neighbors must be between 2 and 6. SP1 is the number of 0, 1 transitions in that sequence as you go around the neighbors must be equal to 1. The product of 2, 4, 6 and 4, 6, 8 must be equal to 0. That is these 2, 4, 6 and the other was 4, 6, 8. And similarly, similar patterns are checked in the next one. So if these conditions are met, you delete those pixels and then replace these conditions with 2, 4, 8, 2, 6, 8, which is 2, 4, that one, and check these conditions. And iterate. Delete those that satisfy this condition and keep iterating until there is nothing more to be done. It does not remove endpoints, does not break connectivity, and does not cause excessive erosion. That's the advantage. So this is the binarized image of a blood vessel pattern that was obtained in the ligament of a rabbit. Some of these projects were conducted in collaboration with orthopedic surgeons. And Dr. Bray was the principal clinical researcher in this project. And the interest, I mentioned collagen fibers. We will see both collagen fibers and blood vessel patterns in ligaments in this chapter and in the chapter 8. The story is that in ligaments, which are connective tissues across the knee joint, taking from one bone to the other, we have the medial collateral ligament and the cruciate ligaments and the the other side, another ligament here, the lateral collateral ligament. So these connect across bones and hold the bones together in the joint. So as we walk, the bones don't separate. These ligaments are made up of collagen fibers, and there is not much blood supply there. So that's why if a ligament is ripped or torn, healing is difficult. But in response to injury, if something happens and the ligament is torn, new blood vessels are formed to facilitate healing. And after healing is complete, those vessels disappear. So to study the healing of the ligament, Dr. Bray wanted to study the blood vessel pattern in normal ligaments and injured ligaments and ligaments that were recovering from rabbit models. And also, the collagen fibers that make up the ligament have an organized structure. I showed you some collagen fiber images with those nearly vertical fibers. Along the axis of the ligament, in the normal case, collagen fibers that are a few tens of nanometers in diameter are like strands of a rope. There'll be some twisting over the length, change of orientation, but if you take a small section, they are mutually parallel lines along the length of the ligament. In the case of an injured ligament, when new collagen fibers are being formed by depositing collagen, that ordering doesn't exist. And the ordering comes a little later. It develops later over the course of a few weeks. So we wanted to study two things: collagen modeling, comparing normal organization, the parallel structure, with scar tissue where there is no structure, and recovering tissue where order returns slowly. That you will see in chapter 8. And blood vessels. There are more blood vessels in the periphery, or what's called the epiligament, on the outer surface of the ligament. But inside the ligament, the true ligament, there are not many blood vessels. In the normal case, they all run parallel to the ligament axis, long axis of the ligament. In the injured case, they are scattered with no direction, no preferred direction, and there are more of them. So here is one of those. Unfortunately, in these experiments, the rabbits have to be sacrificed. When you cause the injury, the rabbits are allowed to heal for a certain amount of time, and to extract the sample, the rabbit has to be sacrificed. Take the sample out. For the collagen fibers, the samples are treated in various ways described in the book and our papers, and they're either cut in cross-section or fractured, and electron microscopy is used to obtain those images I showed, either the collagen fibers along their long axis or a cross-section, those circular images I showed. In the case of blood vessels, black ink is injected into the ligament, and then it is allowed to spread into the ligament, and then the ligament is taken out, it is frozen, and then sectioned using a microtome. There was no microcomputed tomography, but these samples are very small, so even microcomputed tomography can't give us a 3D image. So the sample was sliced using a microtome, and pictures of this nature come up. Blood vessels have the black ink, so they show up. So that is the story, which we will see perhaps a little later, but I have told you the story now. Now we wanted to analyze the orientation distribution of the blood vessels. What is the thickness and what is the orientation? Obviously, there are blood vessels in different directions here. To do that, we did thinning and getting the skeleton. So this is what you have, skeleton. And at each point, we computed the thickness or the area, going back to this image, and then the angle, and obtain statistics of those that I'll show later. So here I just want to show the skeleton. Okay? We're going to 12:30, right? Okay. Now there are several shape factors that have been defined in the literature, and we came up with a few more, specifically for the analysis of calcifications and tumors in mammograms. So a shape factor encodes the nature or form of a contour. The nature of the contour to be encapsulated varies from one application to another. What is it that you want to represent in the shape factor? We will see a few examples. Regardless of the application or what kind of shape factor you get, there are a few requirements. There is a term that is used, they say invariant shape factors. But that's not specific or clear enough. Invariant to what? Invariant to what kind of transformation you have to say. If they're invariant to everything, then they're useless because they're not varying between benign and malignant. So they must vary between benign and malignant and class A, B, C, D, whatever you have. But they should be invariant to shift in spatial position. That's very easy. Whether it is here or there, you should get the same number. Rotation, that's also a requirement. Scaling, whether it is that big or this big, it should be the same. For all squares of any size, the number should be the same. All circles should be the same. That's good. Invariance to reflection may be desirable in some applications, not always. If you do character recognition, you don't want invariance to reflection because we have P and Q and B and P and so on that are reflections of one another. So in character recognition, you don't want invariance to reflection. In mammography, tumors and calcifications, yeah, maybe. But we could reflect the image before you do that. It doesn't matter. So shape factors that meet these criteria can effectively and efficiently represent contours for pattern classification. These are some basic requirements. A very basic shape analysis technique is to fit a rectangle or a circle. So if you fit a circle or fit an ellipse, then you can measure some very basic parameters. Circle, you can say, well, that's the approximate diameter, square the approximate width, but better fit a rectangle. If you fit a rectangle to this, you have the sort of height and width. The ratio, it'll tell you if it is oblong. Is it square or oblong? If you fit an ellipse, it'll give you an eccentricity ratio. How far is it from a circle? That's also a measure of being oblong. So eccentricity or elongation can be measured by using a bounding rectangle or a bounding ellipse. That can be done fairly easily, and you can do some of this using the Fourier coefficients that we will see later. Compactness is a very popular method. It's been around for a few years. The basic initial definition given in the literature was P squared over A. P is perimeter, square it, divide by area of the area contained within the contour, and that gives you a number. Area cannot be zero. If area is zero, it's infinite, but if area is zero, there is no contour, no object. It's just a point, so that doesn't matter. But the problem is this is unbounded. As P increases and A is small, it becomes very large. So you don't have a fixed dynamic range for this. The smaller the area contained by a contour of a given length, the larger will be the value of the compactness. So you can take a piece of string of a certain length, and you can form various shapes. The longer the shape for the same length of the contour, longer in the sense if you just fold the string in half, there's not much area, so it is not an efficient representation of area. If you want maximal area to be contained within that string of a fixed length, then you should make a circle. You get maximal contained area. Now it is possible to normalize this and turn it around A over P square. So if P increases, then compactness reduces. It is not compact. That is, area is small, perimeter is large, it is not compact, it's being stretched. And if you put 4 pi and take 1 minus that, then you have a number between 0 and 1. And if you take a circle, the value will be 0. So a circle is a perfect shape, the most compact shape, the value will be 0, the maximum is 1. So that's a nice normalized range that we have used. It is obviously invariant to shift, scaling, rotation, reflection. All of those conditions are met. So if you have a circle, you get this 12.57, square 16, rectangle 18. You stretch the rectangle more, 25, very sharp triangle 41, and so on. If you take the normalized one, circle has 0, and then 0.23, 0.5, 0.7, increasing. Now, increasing roughness is as you judge it, and you and she may judge it differently. You say something, I say something else. Which one is sharper, or which one is more rough? It's a bit hard to say. Circle is not rough, fine, but between these two, it becomes a bit of a personal preference. So in some cases, you may want to get all your objects sorted out by a number of observers and average the ranking and say that is the average ranking given by a number of human observers. And then check if this agrees. The feature that you have computed agrees, correlates well with that ranking. So my student Liang Shen, for his master's work, he did some work with generating some basic shapes digitally, and also by taking black paper and cutting like children do in kindergarten. We were making fun of him. Prepared those and then computed. Now these were digitized, so it's not digitally generated. No, this is digitally generated, but different circles, only the shape is changing, the radius is changing, the squares, side is changing, and rotation. Rectangles, different aspect ratio and orientation, different types of triangles. And we computed a whole bunch of shape factors and showed how all the circles have 14 point something, all the squares have 15 point something, close to 16. All the rectangles have 17 point something. The isosceles triangles have 22, and the right angle triangles have about 27, plus or minus a little bit. And a few other factors that we will see later on. And then he also did this with paper and then scanned, or digitized I should say, with a camera. And then he ranked these as shown, 1, 2, and so on. This is like a speculated tumor, and put that as 12. But some of you may rank these in a different way. And for these, compactness is going that way, and not exactly in the way he ordered. Number 7 is 0.22, it's going back. It's not, that sequence doesn't agree with this sequence. In some other, depending on which shape factor you compute, that ordering may vary. So which one do you want to choose is a question. You may put all of them together. Moments of several types have been defined in the literature. Moments of images, moments of PDFs we have seen. Moments of PDFs have mean, standard deviation or variance, and skewness, kurtosis, and all those are higher order moments. But you can also take moments of images. You can imagine the image to be like a plate where each point has a different weight depending on how thick it is. So non-uniform thickness plate, where the thickness depends on the gray level. And then where is the centroid? The point where you can balance it, that's the centroid, if you can balance it. If the centroid is within the object, if there is no concavity, then you will be able to find a centroid that is within the object. You can also imagine this as a beam with some load applied, and there is a bending moment. There is a beam supported here, and on the beam you put some weights, and you take moments, the weight times the distance from the point of support. So here, xy are the coordinates, and fxy is the image. So x to the power of p, y to the power of q, fxy, integrated over x and y. That is the order pq of the moment over the entire space of the image, plus minus infinity, but over the space of the image. So there is a uniqueness theorem that says if fxy is piecewise continuous and has non-zero values only in a finite part of the xy plane, then all moments of all orders exist, and that moment sequence is uniquely determined by the image, and the moments determine the image. But we are not interested in reconstructing the image from the moments. We will compute only a few moments and use them in pattern classification as features. So that is a theoretical nicety, but not very important. If you centralize this factor with respect to the centroid, x bar, y bar, which are the first moment m10 divided by m00, m01 divided by m00, then you get the central moments, like the variance. How is the distribution of the weight in this plate of the image with respect to its center of mass? The same thing, these are called mu pq, x minus x bar, y minus y bar to the power of p and q, fxy. So it's like a PDF. Essentially, you're treating the image fxy as a PDF. There is no normalization here, but normalization comes here. So the gray levels of the pixels provide weights for the moments, and you have the coordinates to the power of p and q. Digital image, the same thing, just replace integral by summation. If you compute the moments for a contour, if you have segmented an object like a tumor, there are a few different possibilities. You could say all the points inside the contour are equal to 1 and outside 0. Or you may say, I use only the contour points. I don't care what is inside. So FMN will be defined according to that. If it is the original image, that's the gray level value. If it is a contour that is binary, what do you do with the points inside as compared to the outside and on the contour? So you have some options there. Normally you would just use the contour pixels. The pixels within the contour will be set to 0 and outside too. So there are a number of these relationships. There was a paper by Hu, H-U, and it was a short communication paper, but it has a very large number of citations, very popular, and many people have referred to that. So Hu defined a number of these moments and their relationships. Again, you don't have to remember these. Some of the basic ones you can find, you can determine easily, but the others, let's not worry about that. Normalization is achieved by dividing the moments by mu00 to the power of gamma, where gamma is p plus q over 2 plus 1. So then they are written as mu pq over mu00 to the power of gamma. I said earlier that those were not normalized. This normalizes them. And then who defined these moments? I won't read them. You don't need to memorize them. There's a bunch of moments based on second and third order central moments. 2002 second order and 3012, those are third order. P plus q is 3 here. And more of these, M1 to M7. These are very popular in pattern recognition. We have used them too. They're said to be invariant to shift scaling rotation and useful for pattern analysis, but we found some limitations in analysis of breast tumors and calcifications. I'll show those later on. If you go back to that big table I showed, you will see how they vary, and the moments that we designed don't vary as much. So moments of distances to the centroid is another possibility. We earlier saw the distance dn, square root of xn square plus yn square, distance. So you can take those values and treat them as a distribution and take moments of those. So when a region is represented using only its contour, then do you want to use the contour pixels? Do you want to use the distance? The distance is the signature, like a 1D signal. So statistics of those values. Now we plotted them as a signal by going around the contour once. But there is no, you can just take them as a bunch of numbers and compute statistics. All those radial distance measures. That's what you do here. The distances from the center of a circle to its contour points are all equal to the radius. So the variance is 0. The average value is the radius. So the moments, center moments are all 0. For rough shapes, the distances will vary considerably. So variance and higher order moments of those distance values could be expected to be useful in pattern classification. So it is just this dn to the power of p. For the pth central moment, dn minus m1. m1 is the first moment, which is just the average, to the power of p. That is the pth central moment. Second order moment is the variance. You can normalize, but normalization, there are a few different possibilities. What should be the denominator for normalization of the higher order moments? The pth order moment, dn to the power of p, divided by what? The Ks statistic, Kolmogorov-Smirnov statistics, will use the variance to the appropriate power. This is the variance, dn minus m1 square. That's of order 2. This is of order p. So raise this to the power of p over 2. So this also is of the power p, that is power p for normalization. And then the same for centralized. dn minus m1, this is the central moment. The denominator is the same. Variance, this is the variance to the power of p over 2 for the pth order moment. This was proposed by Gupta and Srinath, and they showed that these are useful in classification of airplane shapes and a few other shapes. But we found some difficulty with this, and we changed the normalization. The main difficulty here is high order moments are sensitive to noise. Noise meaning the contour is not perfect. When you perform segmentation or you try to draw a contour, there'll be some small tremor, especially on high resolution images with pixel size of a few micrometers. Then you need to take care of that, pre-filter, or don't go to moments of very high order. So Gupta and Srinath, they used 4 normalized low order moments. So they said F1 is the square root of the second moment, that's like the variance, divided by M1. That's like coefficient of variation. And M3 over this is like skewness, and that's like kurtosis. Standard statistics. Okay. So Liangshan, my student, he worked on this. We tried to incorporate, we had our own shape factors, but for the sake of comparative analysis and to see if combining our shape factors with others would help, we computed some of these well-known shape factors too, whose moments and those of Gupta and Srinath. But we found that the variations in F2 and F3 for different shape complexity was very small and did not show a good progression from smooth shape to rough shape as we or the user judged it to be. F2 was observed to vary significantly for the same geometric shape, but with scaling and rotation, those circles and squares of different size that I showed earlier. So Liang, he modified F2 and F3, changed the normalization. So all of them are normalized by M1 now, instead of the variance to the power of P over 2. So, and we took the numerator, this is the fourth order moment, we took the fourth root of that. So the dimensions must be the same. So instead of taking variance here and raising it to the half of the power of the numerator, we use mean here and take the appropriate 1/pth root of that so that dimension agrees. And we found this to be better, and we took the difference between them. So we call this MF, F3 minus F1 according to our definition. So let me go back to that. We found MF to be relatively constant in each of these sections, and then increasing monotonically except for these two. Is isosceles triangle sharper than right angled? I don't know. They are both sharp. And for these objects, MF, let's see. No, it's not exactly that, but it's increasing. This is a problem, number 7. It's not in that order. We got the order we wanted using the Fourier descriptors, monotonically increasing. Compactness and moment factors did not increase monotonically. Mostly so. Now here's going back. This is 1, 4, 7, 8, 9. Yeah, this is increasing monotonically. But that's ranking of the shapes by one person. Okay, let's go back here. Yeah. There was another method proposed to take lengths of chords and use them as variables in computing statistics, called chord length statistics. A chord length measure Lk is defined as the length of the line segment that links a pair of contour points, normalized by the length of the longest chord. So if this is your shape, from every point on the contour, you draw lines to every other point and find those distances. They are the chord lengths. Now there is some duplication. You can go this way and come back the same way. So eliminate the duplicates. So all of these lines are taken. Their lengths are measured. Duplicates are removed. And then you take statistics. The same statistics, mean variance, standard deviation, skewness, kurtosis, and all that. And that was proposed in the literature. These are just the KS statistics I mentioned earlier, so I won't go through the equations. Okay? Any questions so far?
In the earlier lecture, we were looking at these specific different shapes. I was thinking tumors of various shapes, but when it comes to the medical aspect of that, for example, if you want to remove the tumor out of that much of a detailed thing that may not come to the practicality level.
True.
Unless otherwise it is taken from just shape perspective, shape analysis, I mean, a very,
True.
very general context.
True. Yeah, the comment is, will the shape of the tumor matter in surgical resection of the tumor? Quite likely, a much larger part of the breast or whichever part of the body it is will be taken out to take some surrounding tissue out without affecting major blood vessels and organs, because the tumor could have spread. So, no, the contour that we obtain or drawn by the radiologist, in practice, the radiologist never draws the contour of a tumor. The radiologist simply says there is a tumor there. And then a biopsy is done by putting a needle, and ultrasound is used to make sure the needle goes in the right place into the tumor to confirm benign or malignant. And then some treatment is applied. It could be chemotherapy, radiation therapy. The resection of that part may not be done unless it cannot be addressed by radiation or chemotherapy. Full mastectomy may not be done right away, but segments of the breast may be removed. And there are some other considerations into how they do that. I can't go into the details of that, but segments of the breast are removed, if not the entire breast. You don't go into just the tumor shape there. This is for analysis to assist in the diagnostic interpretation of mammograms, especially in a screening situation where there are hundreds, maybe thousands of mammograms taken, and every day the radiologist will sit there and in one session of 2 hours may go through 100, 200 patients' mammograms, and each patient or subject will have 2 images per breast, so 4 images from the current session, 4 from the previous, and 4 from the one before that, if the person has been in the screening program for more than 4 years. So 12 images. So look at that, and within a minute or 30 seconds, sometimes, come up with a diagnosis. No change, go home, don't come back in 2 years. Or something has happened, come back for more examination. That's all. But this is more of a theoretical exercise, all right. But if one were to ask, detect tumors and classify them, this helps. For further management, no. And as Dr. Desertel has said, if there are more than 10 calcifications in 1 centimeter square, we'll call it malignant. Whether you detect 10 or 200, it doesn't matter. And similarly, if it is a spiculated tumor with 200 spicules, if you detect 20 spicules, it is spiculated. 200 spiculated, it doesn't matter anymore. Call it malignant, you're done. It doesn't mean that we should sacrifice the accuracy of our method. We should try to be as accurate and precise as possible, but the diagnostic interpretation may not change if I lose 2 spicules out of 50. But I don't want to do that. I don't want to design my algorithm to fail like that. But that's for classification only, diagnostic classification. A radiologist will do that just by looking at it. Now, in a practical situation in Canada, we did all this and published and said, okay, we will develop a package, we will give you, in the screening program, we will give you our programs, and previously it had to be filmed. We said we'll put a monitor. Now everybody uses computer displays. So another display, the original and processed. But the screening program is controlled by the cancer board. There is a very specific protocol. A number of women come there, and it's not to be taken lightly. It's a very serious matter, and I can't just go and stick my computer there. There's a protocol. I can't change that. And then they said, well, all of this is not for screening, but diagnostic application. And in a diagnostic situation, the radiologist has more time. There is already suspicion. And the radiologist will look at multiple things and will spend more time on each case. And will get ultrasound, MR, everything. There they said, we will consider your input. Screening, they wouldn't let us touch anything. The screening films that we got to our lab for digitization, we were not allowed to even touch it. As a member from the screening program came to the lab, my student set up the digitization system, and she did all the scanning and took everything back and deposited. We couldn't even see that. So there are very strict protocols, and they're hard to change. Now, CAD systems that have been licensed by the US FDA, they have passed through all those protocols and tests. They have been put into the screening program. So, but even then, the radiologist is not allowed to look at the output of the CAD system. First, the radiologist has to look at the images, dictate or record the diagnosis, and then look at the CAD system and say, well, I'm not changing it. Or say, well, I looked at the CAD system output now and something else appears, I'm going to change. So CAD is number 2, second opinion. So yeah, all of this, we did decades of work on this. So people often ask me, did you do something useful? Yeah, we added to the knowledge base. Did you put your software in a screening situation? No. And that's not my job. I'm not going to sell this. And I'm not going to prepare a module that can be put there. I'm a researcher. So some business person will have to invest millions of dollars to take this, test it over and over again and get US FDA approval. So the story is more complex than what one can imagine. A lot more complex. Okay, we still have a few minutes. Let's look at Fourier descriptors. We saw the Fourier transform, the DFT and everything. Fourier series you would have seen in your first year calculus or wherever. So you know very well that if you have a periodic signal, you can represent that signal using the Fourier series, which are complex exponential functions or sines and cosine functions at integral multiples of the fundamental frequency or harmonics of the fundamental frequency. But then you go to infinity. You have a large number of those coefficients. Many of the high order coefficients may be very small, so you stop at some point. So here we represent the contour as a complex variable. X and yn are the coordinates in the x and y locations of a discretized contour 0 to n minus 1. The complex sequence Zn is xn plus jyn. So Z is a complex quantity I showed earlier on that contour. We saw the distance dn, but every contour point now is this Zn. It is periodic. Go around a circle, you get the same thing. The magnitude of Zn is the same as dn, that signature of that distance we saw. The Fourier series now, known as Fourier descriptors, is expressed as capital Zk, Zn exponential minus j2 pi over n and k. DFT, that's all. Endpoint, DFT. You have endpoints in the input, you have endpoints in the output. It is DFT, but the interpretation of the coefficients is that these are Fourier series coefficients because of periodicity. And they're called Fourier descriptors. But we let k go minus n over 2 to plus n over 2 minus 1. And because this is a complex quantity, Zn is complex, there is no conjugate symmetry. Z minus 1 is not equal to Z1 in magnitude, like in real signals, in general. So the frequency index k is interpreted as the index of the harmonics of a fundamental frequency, having one sinusoid or two, one period of a sinusoid or two periods and three, and so on around the contour. The inverse is given by Zn, k going minus n over 2 to plus n over 2. So here we said 0 to n minus 1, going once around the contour. But k is indexed this way. And the inverse. So from the Fourier descriptors, you can go back. This is exponential plus j2 pi. So it's reversible. So just a DFT. The interpretation is different. The complex coefficients Zk are known as the Fourier descriptors of that contour. Zk is a two-sided complex spectrum with folding or shifting of the DFT array. The index will run minus n over 2 to plus n over 2 minus 1. The DFT may give you 0 to n minus 1, but you have to index properly. So the DFT may give you index like this, but rearrange it. So k represents the harmonic number. The fundamental frequency k equal to 1 represents a sinusoid in x and y, and differing from spectra of real signals, Zk does not have conjugate symmetry because conjugate symmetry is for real signals. If xn or zn, whatever is real, then there is conjugate symmetry in the Fourier transform. Now, it is not so. The zero frequency or DC coefficient Z0 represents the center of mass, centroid. Z0, the exponential goes away, it is just sum of Zn, average, and X and Y separate, so X bar, Y bar. The fundamental frequency coefficient Z1 and Z minus 1 represents, each one of them represents a circle. So you get two circles, one for Z1 and one for Z minus 1. If you use both of them, Z minus 1, Z1, you get an ellipse. Z0 is the centroid where you put the ellipse. But if you don't care where you draw it, two coordinates will give you an ellipse. One will give you a circle, Z1 and Z minus 1. High order Fourier descriptors or higher order will represent fine details or rapid excursions of the contour. In 1D signal processing, we talk about phase shift or extralinear phase factor with a shift of the time signal. Here, we also have rotation. Rotation of a contour by angle theta may be expressed as Z1n, the new contour is